Right. Today we're talking about continuity. And we've kind of been dealing with functions that have not been continuous everywhere throughout all of our lessons. The limit problems that we've kind of been dealing with are limits that, when we have holes, when limits exist, and we've been algebraically simplifying functions to find the location of the holes. We've also been finding, how functions are behaving around vertical asymptotes. Those are all examples of when functions are not continuous, holes and vertical asymptotes. And for a function to be continuous, this needs to be true. The limit at an x location needs to be equal to the function value at that x location. We use the x location c to make sense of that. Okay, and typically, it just disappeared. You'll see these three types of discontinuities: holes, a jump. Maybe you have a function value, maybe you don't. A vertical asymptote. Okay. And wherever this x location is, we say we are discontinuous at that location, or we have a discontinuity at x equals c. Now, there are two types of discontinuities: a removable, which is a hole, and a non-removable, which are our jumps and our vertical asymptotes. Now, when are functions usually not continuous? Well, usually when the function values don't exist, or when f of c is undefined. When does that happen? Typically when you have a 0 in a denominator. But of course you have some trig functions that you look at that has discontinuities. Most functions are continuous everywhere though. Okay. Here are some functions. We will be asked to evaluate the continuity of the function. Typically, we'll just find where the function is not continuous, just like we found where the limits do not exist. And that's easier than talking about where the function is continuous. Okay, so we have the first function here, f of x is equal to x squared minus 1 over x minus 1. Well, if we want to find the discontinuities, step 1 is to set the denominator equal to 0. If we know when the denominator is equal to 0, we will find where our discontinuity is. Oops. Okay, so I got x minus 1 is equal to 0. In this situation, piece of cake, x equals 1. We know that there is a discontinuity in this function when x equals 1. Okay, but now the question is it going to be removable or not removable? Is it going to be the location of a hole or the location of an asymptote or a jump? Well, here's the deal. if you can remove the problem, if you can remove the issue algebraically, then that's the location of a hole. That's a situation on those limits where, we couldn't find the limit because we'd get 0 over 0, but that means we could probably simplify the function and create a new function, a simpler function, where the hole is removed. You'll find the location of the hole. Boom. That will tell you that you have a removable discontinuity. So in this situation, I'm going to simplify and I notice that this x minus 1 will be removed. That means this function f of x is really the same as the function x plus 1. However, this function will have a hole at x equals 1. Okay, so that's what we got. Well, let's do it for the second function on the right. Why don't we do it together? You guys work through it. I'll kind of freeze the board, do it in the background. We'll compare our answers. Start by setting your denominator equal to 0. You'll have to factor to figure out the locations of your discontinuities. Then that'll help you algebraically simplify things to show you what you have, a removable or a non-removable. Okay, so this is what I got. I got at 0, we have a removable discontinuity, and at -1, we have a non-removable discontinuity, which means most likely this function has a hole when x is 0. The location of that hole is going to be at 0, actually. And then at -1, there's going to be a vertical asymptote. No, sorry, the removable discontinuity will have the hole located at 1. But don't worry about the location of the hole. That's if I ask you the limit question. Now, it's important to remember and write this down. Just because you can remove something algebraically doesn't mean that makes it continuous at that location. It is still a discontinuity of your original function. Just simplifying it helps you figure out whether that discontinuity is removable or not removable. Okay? Still a discontinuity even though I algebraically removed it. It is just the location of a hole. Okay, now this non-removable is a asymptote. The question you might be wondering is, when are we going to know if it's a vertical asymptote or a jump when we have a non-removable? Well, typically with all regular functions written out as expressions of x and just x, we're going to have vertical asymptotes. This is the only type of function that we need to be aware of where you're going to have a jump. And we should be familiar with this type of function. In this function, if you plug in values to the right and left of 3, we should get either positive or -1 everywhere. So if I plug in 4, I get 1 over 1, that's 1. If I plug in 5, I get 2 over 2, that's 1. 6, 1. 3.1, I'll get 1. So we'd have all of these function values over here. To the right of the x value 3 would give me a y coordinate or function values of 1. And then to the left of 3, we'd have negative 1, because the denominator would be negative. Okay, here's a situation where we have a jump. Okay, we set the denominator equal to 0 just to kind of confirm it. That's a non-removable jump in this situation. However, most jumps don't occur with expressions just with x, they occur with piecewise functions. And we'll be asked what the continuity of these piecewise functions are. You know, if we're continuous everywhere, if we have certain discontinuities. Well, let's think about what piecewise functions look like. Typically, we have a domain for all x's that are defined. So we have x's that we could plug in for this function. We'd have pieces that we would use depending on what the x is. And what it would look like is potentially, you know, one piece when x is less than negative 1. And then maybe we would leave this piece and we'd pick up with a second piece right there. And maybe that's a straight line. And maybe that second piece connects with my third piece. That possibly looks like that. Okay, this is what a piecewise function would look like. You know, 3 different graphs that you kind of lay on top of each other depending on what your domain is or what your x's are defined. Well, here we can see we have a jump here where our 2 functions don't meet. But where our 2 functions do meet, we're continuous. And we know that these functions, these parabolas and the straight line, they're going to be continuous everywhere. They don't have like denominators, x squared or 2 minus x. So the question really is, do the 2 pieces of my function meet up? And if they meet up, we're continuous. Here they meet up, we're continuous. If they don't meet up, we have a discontinuity. So here's a discontinuity that becomes continuous. All depends on where one ends and one picks up. So for this guy, all I have to do is evaluate where this guy leaves off and where this guy picks up. And where they leave off and pick up is always going to be defined by your domain. And we are leaving this one when x is 1, and we're picking this one up at 1. So what I do is I consider this like the mini f1, and this is mini f2. I just need to check to see that mini f1 at 1 will meet up with the other guy, mini f2 at 1. So I plug in 1 to both. They equal the same value. They meet up at the same y coordinate. We're continuous there. Check. So this function, this piecewise function, is continuous everywhere. Okay? You guys check this guy. You'll do it. I'll do it. We'll look at our answers. sorry, discontinuity at x equals 1. Okay, my top piece needs to meet up with the middle piece at 1. The middle piece needs to meet up with the bottom piece at 2. I find out that the top piece does meet up with the middle piece. I find out that the bottom piece, the top piece does not meet up with the middle piece. And then the bottom piece does meet up with the middle piece. So we have one discontinuity, we'll have one jump, and that's at 1. Okay? The key is these numbers come from the domain. Any questions? All right. We will be given problems like this where the domain is in an absolute value. It just kind of complicates things. Now, with absolute values, it's important to know that we're talking about the positive or the negative value having to be less than this, right? Positive or negative value has to be greater than or equal to 1. Okay, well, so I'll have x is less than 1/2. Sorry, let me write that out. And negative x is less than 1/2. Okay, those both coming from the absolute value. Well, same thing here. I'll have positive x is greater than 1 or equal to 1/2, and then negative x is greater than or equal to 1/2. Well, if I solve both of these negative x's for x, I have to divide by -1. And who remembers the rule from algebra with inequality symbols when you divide by a negative? You got to flip the symbol, right? If I divide by a negative, this becomes x has to also be bigger than -1/2. So we have like a combo statement. We have x is less than 1/2 and x is bigger than -1/2. Here, for this guy, we'll have x is greater than or equal to 1/2. And when I divide by a -1, I'll have x is, flip the symbol, less than or equal to -1/2. So actually, we have to worry about not just positive 1/2, but positive 1/2 and -1/2. And it's going to be good to use a number line here to help you out. Because when x is less than 1/2 and bigger than -1/2, that's right here. And we're going to be using the sign of pi x right there. And then for this one, when x is bigger than or equal to 1/2 and x is less than or equal to, I guess it's 4, not an and, x is less than or equal to -1/2, we're going to be using 1/2 plus x. So what we thought was just 2 pieces kind of turns into 3. We're going to start with this one, leave it, pick up this guy, then leave that, and pick this one back up. Becomes kind of like an inside function and an outside function that we are seeing if they connect, my inside and my outside. So we have 2 connection points we have to check. We have to check at -1/2 and we have to check at 1/2. So let's do that. I'll check -1/2 first. So I plug in -1/2 into both equations. This is 0. Sine of -pi/2 is -1. So we do not meet up. This is a discontinuity. And then I'm going to check at 1/2. I check, does the sine of pi/2 meet up with 1/2 plus 1/2? It does. So we are continuous at 1/2. Our only discontinuity is going to be at -1/2. We kind of had problems similar to that in the first unit. We're like, where do limits don't exist? It's the same deal. Okay? Yeah.
Wouldn't sine of pi over 2 be 1?
Yes. This is the sign of negative pi over 2, and that is down here, so that's negative 1. The sign of pi over 2 is 1. Okay, cool. And then that's equal to 1/2 plus 1/2. Now, we will be also asked questions, and the question will give us a piecewise function, but not give us all the information. Instead, they will ask us to find a certain value so that the function is continuous everywhere. So this says find the values in the equation so that the function is continuous. What do they mean by values? Well, they don't mean x's because we can plug in anything for x. They mean like this c value or this a value. So what is c? What does c have to be so that function is continuous? Well, for it to be continuous, they just need to meet up, right? Well, if they meet up, then we win. So we need to figure out what c has to be so that x squared minus c and 4x plus 2c, they meet up at 5. So I just plug in 5 to both of the pieces, and then I'll be able to solve for c. So let's do that. I'm going to call the top one f little 1 at 5. That has to equal f little 2 at 5. This is f little 1, f little 2. And this is going to be 5 squared minus c. This will be 4 times 5 plus 2c. It's important that we're plugging these in for x, not for c. We're trying to find c. C is a value. X can be anything. And then we just solve. This is 25 minus c equals 20 plus 2c. Add a c, subtract 20. That's a 5. 5 equals 3c. C equals 5/3. Good luck. Okay, we're going to skip the second one because it's really similar to the other one. Any questions about here? So we are finding the value to make sure the function is continuous. If I plugged in 5/3 into both of these and then examine the continuity, we'd find it's continuous everywhere. Here's another example. This example is used to review solving systems. We got 3 pieces and we have 2 unknowns, A and B. Okay, well, if we went about things, we'd say, okay, to make sure this is continuous, this first line will need to meet up with my second line at 2, negative 2. So I'll say, okay, f little 1 at negative 2 needs to equal f little 2 at negative 2. So that's 6 times negative 2 minus 8 needs to equal negative 2a plus 2b. That's negative 12 minus 8, negative 20. That doesn't help me find A or B. It gives me an equation, but I still have 2 unknowns. I can solve for one of the unknowns, but it'd be in terms of the other one. Okay, so that's going to help me, but I need something else. I need a second equation. I'll need a system. You need 2 equations to find 2 unknowns. So my second one's going to come from the fact that the second piece needs to meet up with a third piece at 1. So you need two equations to solve a system. Two equations for two unknowns. Now, different methods. You can either use the substitution method, which is solve for one variable in one equation, plug into the other. Or you can use the elimination method, which is to stack your equations and then add them together after you've created opposites. I like to call it the stack and add method. Raise your hand if you want me to solve this using substitution. Raise your hand if you want me to solve this for elimination. Let's do that again. I'm going to do one of the two. You want me to show? I can show you both because you know these. Okay? Do you want to see both? Raise your hand. Yeah, because it's been a while. Okay, ready? Here we go. Here's substitution. I take one of these two equations, and if these were x and y's, I bet you guys would feel better about this. But take one of these two equations, solve for a variable. I'm going to take this equation, solve for a. So this is a equals 6 minus 2b. You then take what a is equal to, you substitute it into your other equation. I get negative 20 equals negative 2 times 6 minus 2b plus 2b. You then can solve for b, plug back into one of the two equations to find a. Plus 12, negative 8 equals 6b. Is that right? B is equal to negative 4/3. Okay, substitute that back in to find a. A is equal to 6 minus negative 4/3 times 2. That's negative 8/3. So that's plus a positive 8/3. This is 18/3. So this is 26/3. All right. Not nice numbers, but that's the answer. That's substitution. Okay, remember that? You've done this in algebra. You've done this in algebra 2. Probably did this in pre-calc. Now, elimination. We're going to erase this. Back. Stack and add. We have two equations. If they are equal to, if they are correct equations and they are legitimate, you can add equations together and they will stay legitimate. So I have negative 20 equals negative 2a plus 2b, and I have 6 is equal to a plus 2b. Here are my equations stacked. Now what I will do is I'll multiply one or both of my equations by a number to create opposites. I'll multiply the bottom one by negative 1. That way I have opposites. Because when I have opposites and I add the two equations together, we will get the b's or the a's to eliminate. Here I set it up so that the b's eliminate, and I'm able to find the a's. And just like we found, a is equal to 26/3. You then take that, plug it back in to one of the two equations to find b. I won't do that. Okay? Remember those methods? Nod your heads. Okay? Make me feel okay about our math education system here at Lake Travis High School. All right, good. Here's another one. I won't show you. You'll kind of do it from there. Here is a situation where we are defined everywhere for one function and then just for one point at another one. So I have x squared minus 16 everywhere except for when x is equal to 4. And then when x is equal to 4, I'm going to use b. So the goal is I need to find what b is. Well, if it was easy, if this was just x squared minus 16, you know, because then this would be equal to 0. And I'd say, all right, b has to be 0. But in this situation, if I plug in 4, or this little piece, f of little 1 at 4, I'm going to get 0 over 0, which is undefined. That means that piece, that x squared minus 16 over x minus 4, probably has a hole. And our goal is to find the location of that hole, and that's where b has to be to kind of fill in that hole. We had a question like this on the review of our first unit. So what I need to do is I need to find the limits as x approaches 4 of this function, and then make sure that's equal to f of 4, which is b. Okay? What I'm going to do is simplify this, x squared minus 16 over x minus 4, so that I can have a simpler function to help me find the limits. Once I find the limits, I'll then set it equal to b. Okay, so I have x plus 4 times x minus 4 divided by x minus 4, cancels. Plug in 4, I get 8, and that has to equal b. Good. Another question just like that. We don't have time to do it. Don't even have time for this one. But we do have time to talk about the intermediate value theorem. I'll show you the rest of those examples on the video if you want to watch the rest of the examples. So now that we know what it means to be continuous, we can establish our first theorem that we need to know for calculus, the intermediate value theorem. And this is the theorem. If f is continuous on a closed interval from a to b, and k is any number between f of a and f of b, and there exists at least one number c in ab, such that f of c is equal to k. Seems very complicated, but it's really not. The important thing is that this k value, that's a y value. F of a and f of b, those are y values. C, that's an x value. A and b, those are x values. What this theorem states is that if you have 2 points on a function, you know of 2 points that exist on a function. So here's a point here, and here's a point here. Then I will know that there is some x value between those 2 points. This blue line represents that x value. That when I plug the x value into the function, I will get any y value between these 2 y values at these points, which is here and here. Okay? If you have 2 points and you're continuous between the 2 points, well, you got to connect them somehow, right? Well, when you connect those 2 points, you will always pass through all of the y coordinates between the 2 y coordinates of those 2 points. That's the theorem. If I take this one and I connect it here, and I go like that, well, guess what? Here's that y coordinate. The x coordinate that produces that y coordinate is right there. There you go. And I could connect it however I want to. This could go all the way down here, but I still have to connect it. Maybe the x coordinate is really, really close over here. Okay? But that's the idea. If you have 2 points that have to be connected, no matter what y value you select between the 2 y values of the 2 points, you will find an x value between these 2 points that will produce that y value. Okay? I won't write that down because we don't have time. But does that make sense to you guys? Well, I'll show you an example of a problem that you'll have to do on your homework that is really easy to do. And the question is just to explain why the function has an x value such that f of x is equal to 5. And the x value is going to be between 1 and 2. So we are trying to figure out when this function equals 5. So it's like I need to solve this equation. Well, you're not going to have to solve that equation because that's not what's asked of you. Don't try to find what x is. You can find it. We'll go over how to do it in the future using your calculator. Instead, don't worry about that. Instead, all you need is 2 points. And as long as the y-coordinates of those 2 points are around the y-coordinate of 5, we will win. So let me show you. It's 3:44. The bell is early. Hold on. F of 1 is 4 plus 6 plus 3 minus 2. That's -1. Okay? That is a point. F of 2. When I plug in 2, I get, I'll tell you what I get. -16 or something like that. No, I get 12. Sorry, not -16. I get 12. So if I thought about that, this function has 2 points, one -1 and 2 12. That means I can comfortably say this statement, by the intermediate value theorem, since f is continuous. I know it's 3:45. Hold on. There must exist. Oh, you have to say an f is continuous and f of 1 is equal to -1. F of 2 is equal to 12. There must exist an x value between 1 and 2 such that st f of that x is equal to 5. All right, the rest of the examples will be on the video. All right, let's finish up the other examples. So here's another intermediate value theorem problem. Explain why the function has an x value such that x equals 0 in the interval. We'll say in the interval. The interval is between 0 and pi. All you need to do is find the 2 function values at 0 and pi. If your 2 function values end up being around 0, then I know that I have some x-coordinate that will produce the y-coordinate 0. So the 2 points really, f of 0 is 1, f of pi is -1. So that means I have 2 points, 0, 1, and pi -1. That means no matter how I connect these 2 points, I will have some x-coordinate somewhere that will produce the y-coordinate of 0. So cosine looks like that, and you know that pi over 2 is the answer. But the intermediate value theorem does not care about where the answer is, just the existence of the answer. So I would say, I'm going to type this in. Shrink it a little bit. Since f is continuous, f of 0 equals 1, f of pi equals -1. By the intermediate value theorem, there must exist some x-coordinate such that, and that x is between 0 and pi, such that that function value evaluated at that x is equal to really 0, but I could say, if I wanted to, any value between -1 and 1. Okay, that's what the intermediate value theorem states. Here is a table. Given the table of values, give one value b so that the function must have 2 roots. And the table of values is of a continuous function. what does b have to be so that the function must have two roots? Okay, so I have a bunch of points, but what does b have to be? Well, here's a point -1, 3, -1, 3. I have that point here. Here's a point 3, 5. Here's a point 5, 4, sure. But at 1, I have some point located at b. So maybe b's here. Maybe b's up here. I don't know. But if I have it above the x-axis, well, maybe I connect my points like that. I don't know that I have two roots. The only way I must know that I have two roots is if this point is located down here. And then no matter how I connect, whether I come up, I'm still having to go down here, which means a root is existence. And if we don't remember what a root is when our function is equal to 0. And then even if I come up and really late, I still have to pass through the x-axis twice. So that is why this has to be, -1 or something, -5. Okay. Let's go back up and do a couple more examples. This example, like what does k have to be so that this function is continuous? This, I'd have to find the limit and set it equal to the function. So I'm going to factor the top. Never mind, this is not 3 and 2, this is 6 and 1. Cancel there. I'll find the limit as x approaches 6. That'll be equal to 7. I will set that equal to f at 6, which is 3k plus 2. That's 5/3. All right. I'll set up this one up here, the system. Key is top needs to meet the middle at -1. Now when I plug in -1 into the top, I get +2 is equal to -a plus b. And then if I plug in 3 into the middle on the bottom, I'd get 3a plus b is equal to 6. Now I notice these are kind of set up so that they're stacked. I will have to multiply one of the equations by a number. I can say multiply the top by a -1 so that I create opposite b's, add them together, go from there. This is nice, it's easy to work with. A is equal to 1, plug a back in. B is equal to 3. Okay, so we just found a and b. Final question. What positive values for a is f continuous? All right, so here's the function, and here's a. A is right here. We have x minus 2 times x squared minus 9 divided by x squared minus a. For what positive values for a is f continuous? Well, turns out the answer is none. It's a trick question. Why? Because no matter what values I plug in for a, if they're positive, like 9, well, I will have removable discontinuities at 3 and -3, because I will be able to get my denominator equal to 0. I don't care that they cancel out. They still will be discontinuous at 3 and -3. If I pick another value like 2, well, root 2 and -√2 will make the denominator 0. So in terms of positive values, there are none. But I could plug in any negative values to make this an x squared plus, say, a 1. And then if I try to plug in any value for x, it will always be positive. There will never be any discontinuities because this will always be defined. And if it's defined, it's continuous. Okay? So trick question, but keep that in mind maybe in the future. That's it. Continuity. Thank you. Mr. Esser out.